So let's look at some methods of controlling the fluid flow. If we have control of the flow, we've got control of our actuator speeds. So there are a number of ways of doing this. This is probably the simplest, not the most common. We have a fixed displacement pump running at a set speed. That will put a certain amount of flow into the system, and the cylinder will move at that speed. May have some directional valves in here, but the speed of the actuator is basically equivalent to the flow rate coming from our pump. Now, we can also have variable displacement pumps. So, with a variable displacement pump, the displacement changes, the flow rate changes depending on its setting. We can control its setting in a number of methods, but we can drive the cylinder at different speeds based on this. This is not so common. To be honest, it's very common to have variable displacement pumps, either pressure compensated or load sensing, and the system takes the flow it needs and sends signal back to these, either in pressure or pressure drop signals, and it tells it to increase or decrease the displacement. So the pump is adjusting all the time to give the required flow, but the control and the demand is coming from the system. So that's quite common, but again, not the way the fluid is controlled. So this, another friend, a lovely formula for calculating flows and pressure drops, works both ways round. So most of the time within a circuit we've got a small orifice or a variable orifice within inside a control valve or flow control valve. This is set to a particular size. If we've got a set pressure supply pressure and our load is staying constant, then we're going to get a constant pressure drop across that, which will give us a constant flow, and that's what controls our speed of actuators. If the actuator's load changes, then the speeds do change correspondingly. So there is a version that is pressure compensated, so it always gives the same flow across it, but we'll get to those later, a different calculation. But a nice formula based on empirical data, works very well. Here's another version of the same formula, now giving us the pressure drop across it for a set flow. So if we have a constant flow, we're going to get a constant pressure drop across it. That's another version. So this, using orifices to control our speed, is probably the most common way of controlling things, but there are one more method I'll show you, or two. Closed circuit drives, so very common on mobile equipment, wheel drive systems. We now have a pressure line with a flow coming from the pump into the motor, and a second line bringing it back from the motor into the pump. You'd need an extra flow in just to account for leakages and things. This is very simplified, but this gives us the facility of running in both directions, so both lines can be pressure lines. You can take the pump through over 180 degrees and run the motors forwards or backwards. Nice efficient system, no control valves needed on this one, because we've locked the we've got a good hydraulic stiffness in the two lines. Another one I'll mention, not very common, secondary control, fixed displacement pump, variable displacement motor. Some advanced system has certain advantages, a bit dangerous, it can get carried away with itself with the electronics, so not very common, but you need to be aware that there are a number of different ways of providing flow and controlling your speeds. You need to understand which system you are using. So we like to experiment. Another little test we can do. Here we've got a fixed flow. So if we bring our cylinder down, we're moving at a fixed flow. We'll slow it down, and if we change the orifice size, the cylinder speed doesn't change because we've got a fixed flow. What changes is the pressure drop across it, which we can see in the calculation. So This, if you change things here, you can see your different calculations. Obviously it thinks it's moving. So we can experiment with different orifice sizes. You can put your own values in here. We can switch this to pressure. Now we've got a constant pressure supply, which does give different performance, because now we've got an orifice, fixed orifice, and if we change the pressure, we change the pressure drop across it, which changes the flow through it and changes the cylinder speed. So you not only need to know your circuits, you need to really know your supply system to understand how your flow is being generated if you need to calculate it. And as I say, lovely formula. We like this one. So have an experiment on there and understand it for yourself. See the calculations, put your figures in. One last thing I'd like to show you, which is important if you're changing pipework, adding to circuits. The designers will have calculated the size of the pipes based on a fluid velocity. The fluid velocity within a pipe is very important. It's equal to the flow over the area. And say if you're adding pipes, you'll need to do this. There, as some guidelines, it's different for each system, but as a guideline, suctions under 1 meter a second, supplies 4 to 6, and returns 2 to 4. Now, if you're making one-off systems, you want it to work, no issues, stay with the lower values. If you're doing machines, lots of machines where you want to keep your pipework costs down, but you can actually test the system to make sure there's no issues, you can push to higher values. And lots of issues, lots of reasons why we'd want lower or higher on different machines, but the manufacturers will set these and test these. But yes, stick to pipework, don't go over different size pipeworks in the different areas and designs, and keep, if you can, check it to make sure you're within reasonable limits.